Hello everyone, today we talk about our collision detection on server side. I have Unity booted up and want to show you something. This topic is quite huge, not collision detection in itself, but everything that is involved to make this happen. It's already checked into GitHub, the whole source code, so you can check it out. And we will start unwrapping today the first part that we need to implement, which is basically collision detection itself. We could use the library, but I think for educational purposes, it is best to do it from scratch, and why not? So we have these AoE areas now, which are casted from our boss enemy, and when we are inside of an AoE, we get damage. We have so much health, you barely see it, and we also have some feature where we can stamp out collisions and everything, which I will talk more about in the next videos. But today we want to just talk about how to implement collision detection in 2D. Actually, in 3D, it's not much different, but we focus on 2D and also focus on the mathematics behind it. Actually, I use a new noise suppression to suppress the fan noise of my notebook. Please tell me in the comments if it's better or worse than before. Also consider subscribing to the channel. So let's talk about the separation axis theorem here, where we have the collision algorithm for two polygons. In our game, it's a little bit easier since in our game we do collision between a point, the player position, and a polygon or a circle. The collision detection against a circle is trivial. If the point is closer to the circle than the circle radius, it is a hit, and if it's longer, it's not a hit. For a polygon, it's a little bit complicated, and we even go a little bit beyond that. We do polygon against polygon collision detection, which pretty much basically works the same, but it's just one step more. But when you have understand that 2D collision detection shouldn't be a problem anymore for you. Separation axis theorem also works in 3D, but a little bit more math intensive. And we do it in 2D, but we also will discuss in detail the mathematics behind that. So we have these two polygons, and I can move the green one up, down, left, and right with the markers here, and I can even rotate it. So, and when it touches the blue one, we see it's hit. Simple as that. But the mathematics behind it, or how does the separation axis theorem work, is we need for each of those edges the normal vector, or in separation axis theorem, the axis of each of those edges. And if I do set to true those show axis, I can see the axis of both of those. Let's start with the triangle because it's just 3, it's easier. I render the axis as normal on each of the edges. I render the axis in its own local space, which is basically going through the 0 point, and I render them outside. The reason why I render them outside is just for display purposes, because it screws the optic when you move it outside. But these are a lot of lines, so let's focus on those axes from the 5-sided polygon. Then we have 5 axes. For example, this axis here basically is this one, this long one. This one is that one, and so on. And what we can do, or what the algorithm says, is when you can find an axis where both projections of those polygons doesn't hit, then those polygons don't hit. And when I render the projections, maybe we can find an easy example by rotating them around. So now one of the axes we check hit, and because one is a hit, we check the next axis. The algorithm has an early exit because when one axis doesn't hit, then there's no need to calculate any further axes. So we have this one axis where we have a hit. So we have this axis and we basically project our polygon on this line. So when we check each point where it is on the line, we remember the maximum and the minimum value of those. For example, the minimum value or the leftmost value in our case here is this green point here, and the maximum is maybe here. When we draw parallel lines from when we draw 90 degrees or normals from the axis to each of the points, then we will find the projection on the axis. So it's somewhere here, and the other one is here for green, and for blue it is here, and the other one is here basically. The midpoints are ignored because we just need the biggest space, the projection of the polygon on this line. And those hit because the green line and the blue line touch each other. When we check the other axis here, we see again the projection is this blue one and this blue one, and the green one is here and here at the top. I moved them outside here so we can analyze it. And we see here's a white space between those so they don't touch, then we don't have a hit. And since if only one axis doesn't touch, it is not a polygon hit. So let's also show the other axes and let's create a hit, and you will see that we will find that all axes, the green and the blue one, touch. And if that's the case, then we can see the outside ones. The outside ones are just moved outside. For display purposes, like I said, mathematics-wise, it screws the optics. So that's why I have to render the inside ones. But each of those axes, green and blue, touch with each other. And if all touch, then we have a hit. And this algorithm works and it's pretty robust. So we can even play around with that, rotate. And also with those axes, you can calculate where you have to move the polygons, the basically shortest distance you have to move the polygon so that don't hit anymore. You can calculate that with those axes, but that's something we don't need. So how does the mathematics behind that work? First of all, let me start it again so we see the polygons. First of all, to get an axis or to get the 90-degree value of edge, we basically rotate the edge 90 degrees and normalize the vector. And there's a neat thing in code which you can do when you need a counterclockwise 90-degree rotation. You don't need to calculate it with a rotation matrix. You just do one second. You just do for the x component, you take the minus y component, and for the y component, you take the x component. And this will give you in 2D a 90-degree vector, which is 90 degree to the vector before that. And for the axis, we also normalize that. And to create an edge out of 2 points, it's just 1 point minus the other one. Then you have the edge, and you can take the edge and get the axis of the edge by rotating it by 90 degrees. Because the rest of the algorithm is quite simple, we project the polygons on the axes of the first shape, and we also project the polygons on the axes of the second shape. And if both of them report that they are hit, then we have a hit between those polygons. And the projection basically, we go through each of the axes of one shape, and then we do the projection on that shape. We will discuss the calculus bit behind those projections in a second. And we do those projections, and if those projections hit, we have an interval intersection. If those projections hit, then we check the next axis. If it doesn't hit, we have the early axis that if one axis doesn't hit, we don't need to check any further. Then we switch the shapes around and we check the shape 2 axes against both shapes. That's the whole algorithm. Actually quite simple. If you have a one-dimensional check against the collision on a one dimension, basically on the axis, it's quite easy. If the max value of the max value of A is bigger or equal than the min value of B, and if the max value of B is bigger or equal than the min value of A, we have an intersection. Let's unwrap that one real fast. Let's say we have there are basically some cases which can come in mind. We have one case where A is fully inside B, or the other way around. We have one case where they don't match. A is not matched by B, and we have one where they touch. So these are basically the 3 cases, and the other way around. Basically, if we switch A and B around, doesn't matter. So when the max value of B is bigger than the min value of A, and the max value of A is bigger than the min value of B, we have a hit. So let's check for this one. The max value of A is bigger than the min value of B. The max value of B is bigger than the min value of A. We have a hit. And here we don't have a hit. The max value of B is actually bigger than the min value of A, but the max value of A is not bigger than the min value of B, so we don't have a hit. And it works the other way around. That's how the one-dimensional collision detection, or the interval intersection it is often called, is checked. And then we do for each axis the scalar projection, and if all scalar projections hit, those polygons hit. That's the whole algorithm. I have skipped the part about the scalar projection. The scalar projection of a vector to an axis which is normalized is just the dot product. So you can do the dot product from your point to the axis, and this will work. This is not quite obvious when you don't know the mathematics behind it. Let's dig into the whole mathematics of the algorithm. Let's start with a simple one. 2D rotation. 2D rotation has a rotation matrix of cosinus of the angle in radian multiplied by the x minus y multiplied by the sinus of the angle is the x component, and x multiplied by sinus plus y multiplied by cosinus of the angle is the y component. Then you can rotate a 2D vector around the center point, which is 0, 0. If you want to move it around another point, you move the vector to the local space of the other point, then you do the rotation and you move it back. That's quite easy. And how do we calculate degrees into radian? It's basically the angle multiplied by pi divided by 180 degrees. So 2 pi is 360 degrees. And we consider just 90 degrees because we just want to do a 90-degree rotation and not anything different. And 90-degree rotation is basically sinus and cosinus inserted here in the formula with half pi. So let's check sinus and cosinus half pi. Half pi cosinus is actually 0 and half pi sinus is 1. That's why we can use the short form, because for the x component it is x multiplied by 0 minus y multiplied by 1. So that's why we use for the x component minus y. And on the other side, x multiplied by 1 plus y multiplied by 0 is basically the x component. That's why we can do the shortcut in our case here and take minus y and x and get a 90 degrees counterclockwise rotation on the edge and create the axis. Then we normalize that. So this is very simple, and the next mathematic goes a little bit more complicated, which is the scalar projection of a point or a vector onto our axis. The scalar projection mathematics formula is basically the length of the vector A multiplied by the cosinus of the angle between those. This is the length of A1. The length is the same as the vector alongside this axis. So the length of basically those bar means the length of the vector. So the length of A1 is equal to the length of A multiplied by cosinus of the angle. That's the definition. Let's check how that works. Because let's assume A is completely on top of B. B is the bottom vector here, the axis in our algorithm. Let's say they are completely on top of each other and the angle between those is 0. What we have to expect now is that cosinus of 0 has to be 1, because the length of A multiplied by 1 is still the length of A, and since they are parallel, if you imagine, can I draw another vector? If you imagine A to be this, then you see that the length of A1, which points to the same point as A, should be equal. And the other one, extreme, that we will look into is the 90-degree one. We already know that cosinus of 90 degree is 0. And we see that the projection of a 90-degree vector to our axis would also result in a length of 0, because it's basically a point. If we look at those extremes where we want length of A multiplied by 1, length of A multiplied by 0, and if we can even look into 180 degrees, which is the length of A multiplied by minus 1. And if we check on the cosinus curve, and even better when I rotate this image 90 degrees, we see for 0, for the angle 0, it's 1. For the 90-degree one, which is half pi, is 0. And for 180 degrees, which is pi, it's minus 1. So the extreme values in this little formula work. And the interesting thing about cosinus could be used as a circular interpolation of this projection. For example, if we take a 45-degree value, we will get 1/4 pi, and we have a value of somewhat 175, 0.75 or something, and this will match because the length of A1 is basically the circular interpolation of the length of A alongside this circle. So this formula is not the dot product. And how can we use the dot product to calculate this formula? It's quite simple. First of all, the reason we want to do that is a cosinus of an angle is for a computer a pain to calculate. So we want to get rid of this cosinus, and the dot product will get rid of this cosinus and still be able to do the projection. And this works the following. We have for the dot product, let's say two vectors, u and v, and those have components, in our case x and y, or 1 and 2, but the dot product works for multiple dimensions. You could calculate the dot product for vectors in a fourth, fifth, or whatever dimension. The formula works the same. And the formula is, you take the first part of those vectors, multiply it with each other, and addition every multiplication of the next part, which is in mathematics a sum formula between those indexed entries. So u1 multiplied by v1 plus u2 multiplied by v2 plus un multiplied by vn, and so on. That's the dot product. And there's another definition of the dot product that we take for granted, because deriving this definition is above my mathematic understanding. And the other definition is the length of vector u multiplied by the length of vector v multiplied by cosinus of the angle between those two. Which is interesting because we can control the length of the axis quite easily, because we can normalize the axis. And let's say v is the axis and we normalize the axis, then the length of v is 1. And then we have the dot product between u and v is the length of u multiplied by 1 multiplied by cosinus of the angle between those two. And this is actually the same formula as the scalar projection. Because the only difference between the scalar projection and the dot product, by the geometric definition, is that we need to consider the length of the other vector, in our case b. But since we control the length of b and set it to 1 because we normalize the axis, the formula match with each other. And this way we can calculate the scalar projection with the dot product in the case that one of those vectors has a length of 1. And that's actually what we do, and it's faster for the CPU to calculate the dot product than to calculate the cosinus value of the angle between those two. And that's the neat mathematic performance improvement that we can leverage with the dot product and calculate the projection. And here I have derived it. If we have a dot b, then it's equal to length of a multiplied by length of b multiplied by cosinus of the angle, geometric definition of the dot product. And if b is normalized, then it's length of a multiplied by 1, and we already talked about that. And this is actually the length of a1, which is the scalar projection. That's the whole mathematics behind this algorithm. And now we can do a scalar projection of a vector onto an axis, and we have to do that for each point in the polygon, and we remember the maximum and the minimum, the other way around, the maximum and the minimum value, and then we have the interval on the axis. And that's how the separation axis theorem works, and how we can calculate collision against a polygon, or in our case, polygon against polygon on surface side. The reason why we have to do that on server side is we don't have Unity running on server side for cost performances. So cost is running Unity on the server is extremely expensive. I can't recommend that. The same goes for Unreal Engine or any other engine you're using. If you run the whole engine on server side, there's physics and everything which might your server not need. This is everything I have for you for this week. I hope you understood the algorithm. If not, please join my Discord. I'm very happy to answer any questions there or leave a comment on this YouTube channel or on this video, and I will answer them. I really want to thank you, my Patreon Julian, for making everything here happen and supporting this channel. Have a great week. Bye.